So chapter 1 is the introduction of this class. So again, there's no problem-solving questions, whatever, but it's basically telling you what we're going to talk about. Okay? And many terms you should be very familiar with for those of you who already passed Physics 7C, for example, right? But this time we are more engineering-oriented. In other words, when you solve those engineering problems, they are most likely two-dimensional, three-dimensional problems. Not only just kind of particles. We're going to talk about rigid body as well. Okay? So in this chapter, we're going to quickly go over some kind of simple concept, including mechanics, the forces. There is the static, the forces. What's the next one? What are those four terms? Okay, so we're going to talk about forces. We're going to talk about particles. We're going to talk about rigid bodies. And of course, we're going to talk about two-dimensional versus three-dimensional Cartesian coordinate system. Okay, so in this chapter, I will mention a few things. First of all, what is the mechanics? Well, you learned some kind of mechanics in Physics 7C already, right? Okay, or some other physics courses. But I'm going to kind of giving you some kind of official definition. And we're going to talk about some fundamental concept, some fundamental principle, that's Newton's laws, and the system of unit. This time, we need to pay attention about the system unit as engineering students, or in other words, future engineers. So you really need to pay attention about those units, okay? It's not a big deal. It's very important in practice, okay? Because if you miss whatever some unit problem, that can be a disaster in a way. Finally, we're going to talk about numerical accuracy, okay? When you punctual calculate, you get a lot of digits, but many of them are not very useful. So that's why I basically gave you some certain engineering criterion to take those units more efficiently, okay? First of all, talk about mechanics. Mechanics is the science which describes and predicts the conditions of rest or motion of bodies under the action of forces. Well, it's kind of pretty long, but it doesn't really matter. Mechanics is science. Of course, it's a science because we're here learning something. That's all called science. Okay. Specifically, mechanics is to describe and to predict the conditions of rest. That means statics, or motion. Motion means dynamics. But we're not, in this class, we're not going to talk about dynamics because dynamics is also part of mechanics, by the way. Okay? Not only dynamics, later on also called mechanics, which I gave you the kind of certain category definition, under the action of forces. So if you look at this one, there's a very important term. It's called a force. So this whole class is dealing with a force, in fact. Okay? So we're not talking about mechanics too much. Instead, we're talking about this term. It's called force. Okay? Categories of mechanics, well, all the mechanics traditional engineering people use are based on Isaac Newton's three fundamental principles. Okay? So our first one, second one, and third one. And in statics, we are basically using two of them. It's the first one and the third one. The third one is called the action reaction. First one is called F equals 0. Okay? So these are the two principles we are using. But I want to give you a mechanics concept in terms of different categories because for those engineering students, I believe you need to learn step by step. But this class is the first one. That's also called some kind of engineering fundamentals. Mechanics can be categorized in these three categories. Number one is called the mechanics of rigid bodies. Okay, so rigid body means it's not deformable. However, if you only know this, you cannot solve 90% of problems in engineering. It's simply because, in reality, they're all deformable bodies. Or in other words, the principles or theories are based on the deformable bodies. For example, the chairs you are sitting, and most likely, well, that's deformable because it's pretty comfortable. That's fine. But if you look at this desk, this is, you can say it's a rigid because it's this kind of hard wood made, right? But in reality, when we solve this problem, most likely we're going to treat those as a deformable body. For example, when we talk about those steels, steels or steel alloys are very hard, it's very strong, but they are deformable as well. But in order for you to better understand the deformable body, including those steels behave, you need to know this first. You need to treat those steels, those hard desks, or all the whole building as a rigid body first. And then you'll continue to solve. And I will give you an example later on. So in the rigid body mechanics, we're going to talk about two things. One is the statics, and the other one is dynamics. And this is the one we are talking about right now, which is called the CE30 or MAE30. And then you're going to move to dynamics. Most of you will move to dynamics next quarter. It's called the CE80 or MAE80. After you're done with those, you're going to move to this one, which is also required for all mechanical, aerospace, civil, environmental. And that is called the CE150 or MAE150. That's called the mechanics of deformable bodies. Okay? That is more advanced than this. And all of you, most likely, you're going to take another course related to mechanics, called mechanics of fluid. So C number is 170, I believe. But MAE number, I cannot remember. This is also always 30-30. This is a 150-150. But unfortunately, in the fluid, mechanical and the civil engineering use different numbers. And civil engineering, they call it 170. But mechanical is 130, I believe, or there's something similar. Okay. Anyway, so these are the basic mechanic courses you have to take. They are all required, but this is the fundamental. And compared with 1, 2, 3, 4, at least 4 courses, let me tell you, static is the simplest one. It is one of the engineering fundamental courses. Okay, obviously it's not very easy, but let me tell you, it's not difficult at all. So as long as you spend a certain amount of time, I'm pretty sure you can deal with that. Especially if we have office hours, discussion sessions, if you want to take advantage of those, I don't believe that's the major issue. So of course, I'm hoping all of you will pass. But my experience is, I've been teaching this for 8 years, every quarter there will be some student who cannot pass. And the reason is because most likely they don't do homework, or they don't spend time on those. Then obviously you cannot pass. It's because if you don't want to spend time on those, you spend little time on that, there's no way you can pass that. Okay? And then most likely you have to retake, or you transfer to other majors. Okay? After you finish static, oh, by the way, there's another thing I want to remind you. Most likely, I believe the MAE department still follow another requirement, which is a high requirement. For civil environmental engineering students, for some other majors, I believe if you get any grade other than F, you pass. You can move on. But for mechanical aerospace, I believe you have to get at least C or C minus. So in other words, you got a D, that is the failing grade. You still have to retake it, or you transfer to other majors. Transfer to civil. That's probably okay. Yeah, because you got a D, the civil engineering department say, okay, then of course that's okay, right? But I will not set a different criterion for between mechanical and the civil. So in other words, I treat all of you equal. So when we grade your homework, grade your midterm finals, you're all equal. We even cannot distinguish. You don't have to say you are MAE, or you don't have to say you are a CE. We don't need that, because I already merged the roster, the grade book all together. Okay, so whatever grade you get, that's your grade. So for civil engineering student, you got D just in case. I really do not like D, but just in case you got D, it's a passing grade. But for MAE, you just cannot pass. I'm pretty sure. You check with the department. Okay, so for those engineers, mechanical engineering, mechanical aerospace, you have to work harder. And obviously, civil engineers should work harder as well. So hopefully, you all get the better grade, okay? Okay, so back to this one. Compared with all the other classes, I believe this study is relatively simple. So that's why if you work a certain amount of time every week, and you do this kind of homework, review the book with the examples carefully, there's no reason you cannot pass. Okay? So that's why I do want to encourage you, but on the other hand, you do need to spend some time on it. Okay. I think I have a picture. Oh, that's chapter 2. Okay. Later in chapter 2, I have one picture which clearly shows you something to see the differences between these three. Okay, I'll show you. That's a trust problem. Okay, so in terms of fundamental concept, we're going to talk about space. That means 3-dimensional. So we are going to deal 2-dimensional first. And then we're going to extend to 3-dimensional always. Because the real world is 3-dimensional. You can try your best to simplify a 3-dimensional problem into 2-dimensional. But no, most likely it's not enough. So you have to deal with a 3-dimensional problem. In other words, when I gave you a force, you need to know how to calculate the 3 components of that force in space. So that's why we emphasize 3-dimensional problems, okay? Associated with a notion and a position of a point P given in terms of 3 coordinates measured from a reference point or original. That, in other words, you really have to set up 3-dimensional Cartesian coordinate system in order to solve engineering problems. Okay, always 3-dimensional problems. This one I already mentioned, force, which is the most important concept in this in this class. Force is representing the action of one body on another. I'll give a force. It is characterized by a few things. Number 1, point of application. So the force is applied at where? That's called a point. It's very important. Every time I emphasize the point. Second, magnitude. How big the force is. That's the magnitude. Number 3, the direction. You also need to know the direction because the force is not a scalar. It's a vector. So the difference between vector and the scalar is, let me tell you, today's temperature probably right now maybe 85 already. 85 F, right? That's a temperature. That's called the magnitude. Or you call that's all you have. You need to know 85 F. That's it. Nothing else you need. There's no direction. That's why temperature is not a vector. It's a scalar. You just need to know that's 85 F right now, not in the classroom, outside. However, if we talk about force, or if we talk about a velocity, or if we talk about a displacement or acceleration, they are not scalars, and they are vectors. In other words, when I say there's a force acting on here, not only you need to know how big the force is, 100 Newton or 10 pounds, whatever, right? You also need to know which direction, and that's called vector, okay? So not only magnitude, but also direction. That's to define a force, which is a vector quantity, okay? So it's different. We can talk about all the details later on about forces. We talk about these 2 things. This statics is to deal forces acting on objects. The objects in this class is called the rigid body. In other words, when we see this desk or the tape, that's it treated as object. Not only the object, it's treated as a rigid body. So this rigid body with a certain size, that's with infinite particles inside this. It's called rigid body. But if we want to talk about one point, and that's called a particle. So particle doesn't have a size. We just treat this as one point, a material point. It's called particle. There's no size. A very small amount of matter which may be assumed to occupy as a single point in space. A single point means the distance, there's no distance, there's no size. However, if we talk about rigid body, which we're going to introduce as well, it's a combination of an infinite number of particles. As large may not be enough, it's an infinite number of particles occupying fixed positions with respect to each other. That's in the 3-dimensional setting, but with infinite particles. Okay? In chapter 2 later on, we're going to talk about particles, in fact. So you can treat, that's your assumption. Engineer, being an engineer, you really need to make many but reasonable assumptions. If you want to treat the whole Earth as a particle, that's quite possible. That's exactly what Newton or other ancient scientists did. Okay? The whole Earth can be treated as a particle if we talk about solar system, right? However, this desk is very small. It has to be treated as a rigid body. So it all depends on under certain conditions. Okay, so in chapter 2, we're going to talk about particles with the forces acting on. Starting from chapter 3, we're going to talk about forces acting rigid body. And all the later chapter, we're going to talk about this one. So only in chapter 2, we're going to talk about particles. The reason we need to do this, force acting particle, is because this information. So that's why we spend a certain chapter 2, to talk about forces acting on particles. And starting from chapter 3, we're going to talk about rigid bodies. Okay? There's some other comments I want to make in this chapter 1 before moving to chapter 2. As I said, there are 3 fundamental principles, okay, developed by Asian scientist Isaac Newton. Okay? Even now, we're still using that. Number 1, Newton's first law. Newton's first law is very simple. The description is like if the resultant force on the particle is 0, then the particle will remain at rest or continue to move at continue to move in a straight line with a zero acceleration. In other words, F equal to 0. That's Newton's first law. You all learned in the previous college physics, right? F equal to 0. It's not that simple. Number one, F equals 0 indicate what? 3 equations, not only one. You say, oh, F equals 0, that's one equation. No, because F itself is a vector. In 3-dimensional setting, that's 3 equations. Okay? Second, in each equation, Fx equals 0, or Fy equals 0, or Fz equals 0. Is that simple? It's not simple either. But in this class, we're not going to talk about something further. Later on, when you take 150, some other structural analysis classes in aerospace or civil, you will see Fx equals 0 is a differential equation. It's not the algebra equation, okay? Because F itself is unknown. So F equal to partial something, partial space. So that's why Newton's first law, at the beginning you see, wow, that's very simple, F equals 0. It's really not that simple. Okay? So number one, there are 3 equations because of the space issue. Number 2, they are in fact differential equations. Differential equation means what? It's much more complex, right? Compared with the algebra equation you learned in high school. That's why many times later on when you take those engineering courses, you are required to take those more advanced mathematics class. I don't know, differential equations is a math what? Math 3D or 4D, whatever. But anyway, those are the courses you need to take. But in this class, we're not going to talk about that part, okay? Second law, simply F equal to ma. So F equal to ma, we're not going to use because this is dynamics one. I just want to mention this equation, number 1, is 3 equations as well. And number 2, this right-hand side can no longer equal 0. This A is the acceleration. The acceleration itself is a derivative, second derivative in terms of time. So this one obviously is more complicated than the first law. So that's why statics is simpler than dynamics. Okay? I can give you a lot of more suggestions later on. But one thing you need to know, if you really have a hard time or if you're not working hard, I would suggest you to change to some other majors instead of wasting your time. If you want to be an engineer, you are committed to spending a certain amount of time to deal with those things. So statics, in general, is simpler than dynamics. So that's why in dynamics, you're going to take later, it's going to be more challenging. So you need to be prepared to make sure you are committed to spending more time in those engineering courses in order to be successful as an engineer. Newton's third law is something we want to use as well in this class. The forces of action and the reaction between 2 particles have the same magnitude and the line of action, but with the opposite sense. The direction is different, the opposite. So in other words, when I gave a force acting on this point, then this point from this wooden object gave me a reaction. The same magnitude, but in a different direction, opposite direction. And that's Newton's third law, which we're going to talk about as well in 3-dimensional setting. Okay? Yes, this is the picture I want to say. To distinguish those 3 classes, for example. Okay? So what is objective? Now, I gave you those descriptions in writing, right? But actually, it's better to look at some pictures. Okay? So this is the real picture, I believe, somewhere across the river. A pretty wide river, right? They didn't say anything. Okay. So let me tell you, after you finish this class, or after you finish chapter 6, which is called trust, you should be able to calculate the forces for this structure. Okay? It's not difficult. But of course, now we haven't talked about the details yet. So with this kind of a bridge, this part, or even this part, the support, are what we call the truss. So you should be able to calculate force members in each truss member. Each one is called the truss member. You can calculate the force using statics, this class. However, in engineering design, that's not enough. Because later on in chapter 6, when you review all the details, okay, you will not see the difference if I use a steel as this truss member versus I use a rubber as this steel member, as this truss member. And you all know that. Nobody used rubber. Right? And nobody even used a wood to design this bridge. Why? Well, this class, cannot tell you why. Well, you know the answer because from your common sense. However, if you continue to back. However, if you continue to learn this one, I hope you can answer yourself by saying rubber is no good, or wood is no good to be used for steel trusses. This class just tells you how to calculate the procedures, those forces acting in each truss member. They're not going to tell you the difference between a steel and a wood or a rubber. Then you say, well, okay, is that not important? Well, you have to learn this first to calculate force. And then you divide it by something, you're going to transfer back to the specific engineering materials. And normally, if you see steel is fundamentally different from wood or different from polymer or rubber, it's because what? Because the stiffness, or it's called the Young's modulus, are very different from each other. And that is something you need to learn from other courses. Okay, so hopefully, by this picture, where's my, here. You know some difference. There's not all the difference there. I just want to show you a picture, right, to see the difference between these two. Now, what's the third one? The fluid, right? Fluid mechanics. Why fluid mechanics is important? Well, let's use the same picture. The fluid mechanics talks about something with the fluid. That's a river, for example, right? Water. So when you see this support here, that's called the foundation. Okay? So normally, we provide the reaction due to traffic load, due to wind load, or due to earthquake even, right? If you do not know fluid mechanics, you really cannot design much about the foundation. You can make assumptions by using statics and the deformable body of mechanics. That's fine, but it's not very accurate. You have to know the fluid with the velocity so that you can apply a shear force, not only the compressive force or normal forces. So that's why the fluid mechanics is also important. Okay, so with this picture, hopefully you know the difference between statics, mechanics, deformed bodies, and mechanics of fluid. Okay, but you should be very optimistic because just spending a quarter, 10 weeks, you can somehow solve this problem. So you should be very proud of this. So at the end of the class, if for whatever reason you still do not have no idea about solving the truss member forces, you need to ask me. Okay, each chapter, I hope I will give you a picture. Each chapter, I will give you one picture. Just tell you, by the end of this chapter, you know how to solve that kind of problem. Okay? But this chapter 1 is the introduction. I give you more pictures. This is another picture showing you something related to statics, right? So this is a handicapped man trying to reach the weight. Okay? So normally, in order to design this artificial muscle or prosthetic arm, for example, you need to know, in order to design that, right? You need to know the forces applied on there. So normally with this certain kind of picture, by assuming rigid body with a certain weight, you can calculate from this class. Because three-dimensional setting, in fact, right? You can calculate the forces needed in this prosthetic arm, and then you can design. Okay? Of course, static is the basic one to calculate the force. But in order to carefully, using engineering design principles, you need to calculate something further, which is called the stress. But we're not going to talk about stress in this class. We're going to talk about force. But force divided by the cross-section area, that's the stress. And then you divide it by the Young's modulus of the material, it becomes a deformation. And that is very important for us to know. Okay, there's another one related with aerospace. Okay, this is, anyway, this is aerospace somewhere outside the Earth. You see, when you have this is also kind of a truss, or you can call the beam. Anyway, so design the joint, this is the joint, and support here of the shuttle remote manipulator system, which is called the SRMS. I hope some aerospace engineer students know this kind of abbreviation, so that it can be used to pick up. You see here, you need to pick up something from here, and then the support with various payload. So these are look at quite complex, but in fact, if you simplify using some static concept, you can calculate the force as well. And the other thing, mechanics very important, or statics, or deformed body is important is, you know, recently, early this summer, I forgot, is it early this summer or last summer? I forgot. You know, the JPL has the Mars program, right? They send the Curiosity rover there. The difference between previous rovers is this time they can pick samples on site. They never had this kind of thing before. In the previous years or decades, right? They sent some kind of rovers into the Mars, but they just some kind of take pictures and send those pictures back. This is the first time, I forgot, this summer or last summer, I cannot remember exactly, very recent, in a year. The Curiosity 1 can sample on the surface or a little bit underneath the Mars surface. Unfortunately, they cannot come back. You know what they do? They sample those, they took those samples, the rover using the arm, took the sample, and then do the chemical analysis on site. And then they send the result back. Unfortunately, they cannot send the sample back, right? But at least they can do that. And those chemists are very good in terms of doing this. But there are some problems at that time. Probably they didn't do it very carefully. Hopefully there are enough engineers who can help them with that, but it was not the case. You know what? When they use that arm to pick the sample, there are some problems because they need to have a drill, right, to go into the surface and to get a sample in and then do the on-site analysis. There's a vibration that's related with mechanics. And the vibration is so big so that the rover may not support themselves on Mars. So that's why there's some kind of mechanical or structural engineering problem. They did not pay too much attention. And there's some kind of problem. Of course, in the future, they're going to fix that when they send another one later. So what I'm trying to say is chemistry, biology are important. But mechanical engineering, aerospace engineering, civil engineering are not that are also very important. Right? So being an engineer, we should be very proud of that. Okay? Anyway, back to this. There's a lot of things you can do just based on the fundamental principle you are learning now, and you are going to continue to learn. Okay? So I have 2 more slides, or maybe 1 or 2. 2 more slides. I know I'll let you go. Okay? So the last part is the system unit. This is also important because being an engineer, you really need to pay much attention on this. And that is to set you fundamentally different from scientists. Because scientists, many times, they may not pay too much attention on the unit. But you are dealing with all the numbers. But keep in mind, as an engineer, you write a number. That's not enough. You must write something additional right behind the number. And that's called unit. And that's very important. Okay? So being a US engineer, you have to learn more compared with other international engineers. Because US now is still using the 2 systems. That's kind of unfortunate, but that's the truth. So you really have to know both. So all the questions later on with homework, whatever, you have to sometimes deal with international unit system. You sometimes have to use the US Countryman unit. Okay, you have to know both. Anyway, so international system of units is called the SI system. We use a meter, second, or we are now using second in the static. In dynamic, we use that, and the kilogram, and then also Newton. That's a force. This is very important. I want to emphasize every time. When I say object self-weight, if the self-weight of a body of mass is 1 kilogram, for example, or 10 kilograms, don't use this as the force. That's called the self-weight. But we always deal with self-weight because when we talk about the rigid body, normally it's heavy. We have to use self-weight. You need to make sure you use this simple equation. This m is the weight in terms of kilogram. You need to multiply with this g, which is 9.81, in order to transfer from kilogram to Newton. So we are only allowing you to use a Newton in international unit system to deal with those engineering problems. Okay? So make sure every time you multiply with 9.81 in order to treat this as a force. Because self-weight, in fact, is a force. But you just need to multiply with 9.81, and don't forget. Okay? If you are dealing with a US unit, then you don't need to worry about 9.81, because then basically they use in terms of pounds. The self-weight in terms of pounds is already a force unit, so then you should be very happy with that. Okay, so whatever pound, 10 pounds or 20 pounds, you just go ahead to use that directly as a force. But later on, when you move to dynamics, then you might need to pay attention about this equation. The pound is not the self-weight unit in terms of mass. Then you need to divide it by 32.2 as a unit in the US system for G to get this mass. But that's another course. I just want you to pay attention. So international unit, this is something you really need to know in this class. For the US system, you're going to worry about that later. Okay. The last slide I want to say, that's his last statement, but it's also very important. You need to follow this one. That one is the digit, the numbers you get after you punch your calculator. Because all the calculators gave you like what? 8 digit, I believe, right? Well, some good calculator can give you 12 or 16 digit. In engineering practice, there's really no need. There's too many digits. They are not accurate. So as an engineer, you need to know this kind of policy or specification you need to follow. So this book, try our best to follow. As a general rule for engineering problems, the data you got from calculator, so those data are seldom known with an accuracy greater than 0.2%. This is kind of like rules people develop in engineering. Okay, I don't know exactly why it's less than greater than 0.2, even why not 0.3. But let's keep this one. As a result, therefore, it is usually appropriate to record the parameters beginning with 1 with a 4 digit. So your final answer, if the first digit is 1, you need to keep 4 digits from your calculator. Okay, so 4 digits, that's your final result. But in the middle process, you need to keep what? 5 digits if the first digit is 1. But many times the first digit is not equal to 1, that's fine. Anything rather than 1, 2, 3, 9, right? So then your final answer should be with a 3 digit. In the middle process, you need to keep 4 digits if the first digit is not 1. For example, this is a good answer for a final answer for a certain force. 40 times 2 pounds. Because there's a 3 digit. The reason you just keep 3 digits because the first one is 4, it's not 1. But sometimes when you deal with a 15.58 pounds, then you need to keep 4 digits because the first digit is 1. In the middle process, you need to keep 1 more digit so that the result is still accurate. But you really do not need to write too many numbers needed. There's no need. So you punch your calculator, just use those meaningful numbers.